Alrighty, so today we're going to be talking about the Dirichlet formulation for your three-dimensional panel method. And this is where we really start to exploit some of the really theoretical aspects of this, and where it really pays off in knowing the mathematics, knowing what's going on behind the scenes, and knowing this is more than just slapping some elementary potential flows together. This is why we really looked at Green's functions and all that stuff, or Green's identities and all that stuff. So let's dive into it. If you remember, I said before that if I enforce the zero normal flow boundary condition everywhere on the surface of some configuration, let's go ahead and draw that out. Assuming OneNote's going to keep up with me here. There we go. If I enforce the zero normal flow boundary condition on that, that is equivalent, or what that will lead to is my total inner potential being some constant inside. Okay? Now today we're going to show to a certain extent why that is. Well, I guess no. We're going to derive a sufficient condition for this. Not necessarily a sufficient and necessary condition, but we'll show that having this inner potential be some constant leads to the zero normal flow boundary condition. And then we'll show how we can use that to actually calculate our flow solution without ever having to calculate velocity influences. We're going to do this all in terms of potentials, which is why we call this a Dirichlet formulation. Okay? So recall that our boundary condition is v dotted with n is equal to 0. And if you recall, v is the gradient of our scalar velocity potential. And if we take the gradient of the scalar velocity potential and we dot it with the normal vector, then we get the derivative of the velocity potential in that normal direction. So this is equivalent to saying partial phi, remember we're dealing with the total potential here, partial n is equal to 0. Now, if you remember, we talked about in one of the previous videos that mu is equal to the difference in perturbation potential between the inside and the outside. So phi, little phi minus phi, or it's also equal to big phi minus big phi. So it's the difference in total potential and the difference in perturbation potential, because our free stream potential is the same on both. It's the exact same thing with source strengths. The source strength is equal to the difference in normal derivative going from, gee, I hate it when it does that to me. Oh, come on. It's the difference in the normal derivative of velocity potential when we go from the inside to the outside, both in terms of both in terms of perturbation potential and in terms of total potential. Oops, that's supposed to be a capital phi. Okay, and for this formulation we're choosing not to deal with sources. So we have that this is everywhere identically 0. And so using that and this condition here, we're going to say that partial phi partial n is equal to, these are total potentials again, partial phi I partial n. Okay? Because we said that's equal to 0, we can bring one over to the other side and we get this. And now, what we've also said from before, enforcing our zero and overflow boundary condition, is that this is 0 everywhere on the surface. Okay? Now let's go ahead and rearrange things a bit in terms of this inner potential. I can write grad phi I dotted with n is equal to 0. Okay? Now I know I made this step towards the partial v partial n, and now I'm taking a step backwards. That's totally fine. We can swap between the two as we like. Now, if I want this equation here in blue satisfied, I'm sure there are numerous different ways to do this, but, well, maybe not, since phi satisfies the Laplace equation. But anyway, at least as far as the information we have here, a sufficient condition for making this blue equation true is that we can simply state that grad phi I is equal to 0. Okay? You can see that if grad phi I is everywhere 0, then dotting it with the normal vector isn't going to change things. The result of that is still going to be 0. Okay? So I have a sufficient condition whereby if I can say that grad phi I is equal to 0, then this blue equation is satisfied, this red equation here is satisfied, and I satisfy the zero normal flow boundary condition. Okay? Well, if the gradient of phi I is 0, then that simply leads us to the basic result that phi I is equal to some constant, which is what we've had before. Okay, we're going to arbitrarily choose our constant to be 0. You're welcome to choose any other constant you like. It just introduces a constant, so there's an extra addition there that you don't need. But we're going to choose this constant to be 0. So we choose C is equal to 0. And what that means is that the total potential on the inside of the configuration is 0, which means that the free stream potential plus the inner perturbation potential is equal to 0. Now, what is our free stream potential? Well, we have the condition that the gradient of the free stream potential is our free stream velocity, v infinity. Okay? Now, I won't go through a rigorous derivation to get to this, but from this I can simply say that phi infinity is equal to r, which is a position vector, so consider r to just be a point xyz, dotted with v infinity. Okay, and so if we write that out with its components, then that's x times vx plus y times vy plus z times vz. And if you take the gradient of that, well, taking the derivative with respect to x will only extract this term, and it'll be vx. Taking the derivative with respect to y will only extract that term, it'll be vy. And taking the derivative with respect to z, it'll extract that term, it'll be vz. So we can see that if we take the gradient of this quantity here, that'll give us our free stream velocity. Okay? And I guess I really probably should put little infinities right in here on these vz, vx, and vy, but we'll forego that for now. So anyway, so we have this formula for our free stream velocity, or our free stream potential, and so we can plug that into this equation that we have right here, and we'll say that r dotted with v infinity, and r is whatever point we're looking at. So if I want to know the point, or the potential at point xyz, that's my r, plus vi, and I need that to be 0. in order to satisfy our zero normal slope boundary condition. So if I do that and I just rearrange things, then I get to the conclusion of Vi needs to be negative R dotted with V infinity. And that's all it is. Really quite simple. We can say that if our inner perturbation potential satisfies this equation everywhere inside the configuration, then our zero normal boundary condition will be satisfied and we'll have our flow result. Pretty slick, right? We've never actually really had to consider velocities much. I mean, there's this explicit free stream velocity term, but we're not having to calculate velocity influences or anything like this. We're doing this entirely in terms of potential. Now, how do we turn this into a useful system of equations? Well, let's think about n unknowns and equations. Our unknowns is over each panel we need to know what the doublet strength is, and we have one doublet strength per one panel. That means we need to apply this equation as many times as we have panels. So what we're going to do is for each panel, we've got our normal vector n. What I'm going to do is I'm going to take a control point and I'm going to offset that control point from the centroid of this panel in the direction opposite of n. So this is my P centroid, and this is my P, that should be P sub C2. We'll call this P control, okay? And this offset parameter is something that I get to pick. I'll call it L. And you're welcome, and this is a fun exercise to do. Once you get things implemented, fiddle around with what L is. See how small you can get it before your results start going bad, see how big it can be before your results start getting bad. You'll find there's a happy medium. At least that's been my experience. It's a really interesting parameter to play with. I find the closer you can get it to the configuration surface, the better, but again, there is some point at which it breaks down. So what we're going to do is we're going to loop through each one of these control points. And for each one of those control points, we can write out the equation that we want our inner potential, our inner perturbation potential, to be equal to negative P control dotted with V infinity. Well, what is our inner perturbation potential? It's just the sum of the induced potentials from our doublet panels. So we get the sum over n of mu, of mu, so the doublet strength of panel I, times phi, I'm going to call this phi induced, so phi induced by that panel at that control point is equal to negative P control dotted with V infinity. Okay, so this should look familiar. This is kind of similar to what we did with the Neumann formulation, but just a little bit different. Now, if I introduce a little bit different of nomenclature, and I say that I'm going to index my panels, or I'm going to index my control points in I, and then my summation over the panels is going to be J, then I can write this equation in a slightly different manner, and that maybe might look a little more familiar. Sum, oh come on, the sum, oh come on, write a sum for me. My pen does not like this half of the screen, I don't know why. The sum from J equals 1 to n of mu control point I is equal to negative control point I dotted with V infinity. Okay, so for each row of my equations, and you can see that we're going to turn this into a matrix equation, for each row I'm looping through control points, and for each column I'm going through panels that induce a potential. Okay, so if I want to take this, excuse me, and gather this all up into a big matrix equation, I'm going to end up, well, this is phi1 at control point 1, phi2 at control point 2, so on and so forth. This is going to be mu1, mu2, so on and so forth, equals negative p1 dotted with v infinity, negative p2 dotted with v infinity, so on and so forth. Okay, so you're going to build up this system of equations by calculating your unit induced potentials at each one of your control points. Well, you need to place your control points first, so create an array that stores all of your control points for each panel, for each of your panels, and loop through those, calculate these induced potentials, put it into the matrix, and then you can solve this matrix equation. Now, with this one, you won't get an error if you just pass it to numpy.linouch.solve. And that's because we've taken that arbitrary constant into account. With the Neumann formulation, we didn't take into account that the inner potential can vary by some arbitrary constant. And that's why the system of equations ended up being singular. Here, we've explicitly said we want that constant to be 0, and that is baked into these equations here. And so this system is actually not singular. And so that's that's kind of the really fascinating thing about this, is that, you know, just by reformulating the equations, you'll notice that your outputs are almost exactly the same. You know, it's going to be basically in the numerical noise that you notice any difference between the Dirichlet and the Neumann formulation. But just because we've reworked it a little bit and approached it from a different angle, the Dirichlet formulation is well posed, whereas the Neumann formulation is not. And so we get a good solution out of the Dirichlet formulation without having to use least squares or anything like that. Okay, pretty remarkable. The nice thing about this is that we still have the exact same inner potential as we had before. Again, we have the phi I, big phi I is some constant. And so as with the Neumann formulation that we had, we can still calculate our surface velocities just using the gradient of the doublet strength on the surface. So same thing as you did before. It's just now a different way to get those doublet strengths, but all the post-processing is the same. Okay, well, this is the last lecture video. I'll be recording one on the extra credit portion, of course, but for those of you who don't do the extra credit, I hope you've enjoyed this, and yeah, good luck going forward.